Hello, welcome to Hyfindr Tech Talks. My name is Steven, and it's our goal here to understand the technology behind the hydrogen economy. Today, we are going to focus on hydrogen production and carbon intensity. Now, that's a very interesting topic, can go all sorts of ways. We're going to look at it from the technical perspective only, so this is not political, this is just really tech. And for that, I have somebody who's got a bachelor's, a master's, a PhD in chemical engineering. He has worked as R&D chief executive in several companies, is now fortunate to, or BayoNet is now fortunate to have him working for them as their chief innovation officer. Greg Powers, welcome to Hyfindr Tech Talks.
Thank you, Stephen. I'm really thrilled to be here. There's a lot of important information that I think the society at large needs to learn as the hydrogen economy comes in. So this is a great opportunity for people to learn some of the lingo and understand some of the choices we make when we're trying to create a hydrogen economy for mobility.
Yeah, thank you very much, Greg. So again, just want to say it again, we're going to be talking, chemical reactions and different ways of doing it. Not judging or but this is, we just take it from there. And thanks, Greg, for taking the time for this. So, first of all, hydrogen production. I know for you this must sound really basic, but what are the ways that we can even produce hydrogen in a useful way for the economy?
Yeah, actually, there are quite a few ways. And the technology in all of the ways to make hydrogen is actually quite old. Some of it has not been commercialized very much, but fundamentally, any molecule that has hydrogen, which includes many, many of the molecules around us, can be deconvoluted so that the hydrogen can be extracted. So, for example, electrolysis uses electrons to split the hydrogen and the oxygen in water. Steam methane reforming uses heat to split the hydrogen that's connected to a methane molecule. Nuclear and coal can do the same thing as steam methane reforming, just with a different source of energy. But fundamentally, you can gasify coal, and there's a lot of hydrogen in coal, but it's a not well favored process because of its, it's very hard to clean up. It's expensive to operate. So right now, the two main, if you let me go to the next slide.
Yeah. Before you do so, can I ask you just sure. Out of personal curiosity? So, I mean, even though it's not one of the main ways, how does one make hydrogen of nuclear power?
Well, you use the heat. You can either use the heat to make electricity and do electrolysis, or you can use the heat to run a steam methane reformer. So in a way, it's just one of the sources. Making hydrogen per se from nuclear it's not necessarily a byproduct you want to try to extract from the nuclear reactions themselves. You're using the reactions to create heat or electricity.
Okay, all right, understood.
So the two main hydrogen production routes that people talk about are steam methane reforming and electrolysis. And again, steam methane reforming is a process that runs on heat. Electrolysis is a process that runs on electricity, so current. Now, steam methane reforming dominates the hydrogen manufacturing landscape around the world. It's over 95% of the production of hydrogen comes from steam methane reforming. Electrolysis hasn't really been deeply industrialized and commercialized for hydrogen making. It's used for many other molecules, but for hydrogen making, it's still just now emerging from the research phase into a development phase for what's the optimum configuration and minimum amount of energy. So it has a very small fraction of the manufacturing market right now.
Mm-hmm. Well, yeah, understood. I mean, clearly, I think electrolysis is, it's if you look at the current discussions, it's in a lot of people's mouth, which is great. I mean, but considering the fact that there's this large part of the market still running on the other one on steam methane reforming, I think this is a good opportunity to look into this, and I think this is also where you have some expertise to share and some products that you're offering.
Yes, yeah, and the SMR is a very interesting. Maybe I'll turn to the process.
Yes.
And talk about what steam methane reforming is.
Yeah.
So it's literally what it says, but it's actually a little bit more than people think. It's actually a two-step process. There are two chemical reactions. So if you let me get my pointer out. Oh my. Hang on.
No worries, no worries. So, Greg, we know you're an expert in chemistry. You've basically gone the whole way. You do not need to qualify in the same manner with software for presentations, but you're doing a great job.
I wanted to get a pointer.
Pointer, okay, but okay, it's fine. You can just use the mouse.
Okay. Mm-hmm. I should have done that in the beginning. Okay, so if we go back to this slide here. A quick outline of what steam methane reforming is. Actually, it's a two-part reaction system. The first part is natural gas, following my cursor, joined up with steam. So this blue vessel is basically a steam boiler.
Yeah.
And there are many, many different ways to do these things. You mix the natural gas and the steam, and then you heat them up. And they have to be heated to a very high temperature, almost 900 Celsius. Mm-hmm. So it's a very, very hot reaction. It's facilitated by a catalyst. And there are many different kinds of catalysts. A catalyst is something that you add to a reaction to make it go faster. Mm-hmm. Mm-hmm. So the idea of steam methane reforming is a fast reaction at a very high temperature. And what the product of that step, the reaction step number 3, is syngas, which is hydrogen and carbon monoxide. Yeah. And then there's a second reactor. We didn't label it here, but this is called a water gas shift reactor. A little bit more steam is added to the syngas, and the water reacts with the carbon monoxide to make another hydrogen. So, and then we separate it out on an adsorptive separation system. This is a very common industrial process, kind of an off-the-shelf kind of thing.
Okay.
So the way the stoichiometry works is one methane creates 3 hydrogens from the first reactor and 1 hydrogen from the second reactor. And then at the end, all the carbon that comes in as methane goes out as CO2. Mm-hmm. So 1 methane, 2 waters, 4 hydrogens, and a carbon dioxide. Mm-hmm. So that's what's coming out. And there's a little bit of a recycle stream here that we use because some of the things that come through that are rejected from this separation process get recycled back into the process.
Okay.
So we try, the process is intended to be very efficient. And over the years, the processes have been made very large. And now, why is that? Steam methane reforming up till now has been used as a chemical reactant. So, for example, the making of ammonia or inerting during steel making, or in plastics. A lot of plastics come from hydrocarbons, oil-based hydrocarbons, but they need more hydrogens to become plastics. So virtually all of the world's hydrogen is used in a chemical reaction. And as such, the model is to get the factories as big as they can, because these are very large consumers of industrial chemical ingredients. And my discussion today is going to lead us to a discussion about mobility. Mm-hmm. So now that's the way the reactions are generally run. The way BayoTech is doing it is in what's called distributed steam methane reforming. So as I said, the traditional factories are very large, usually situated right next to, for example, an ammonia making plant. Mm-hmm. And the goal is through the pipeline, the hydrogen goes across the fence and goes into that reaction. Mm. Our mission is to make hydrogen on a much, much smaller scale and make it located in more places, because the hydrogen mobility market is not going to be in just a very few places. In the US, it will be widely distributed. So as a result, we had to create a reactor that was very efficient, because it's not got the opportunity to take advantage of scale. Chemical reactions can generally be made more cost effective the bigger you make them.
Is it?
So we've done something that's contrary. We're making the units smaller. And how do we do that? So we're doing that with this concept called a BayoNet reactor. And if you go back to that schematic in your mind, the methane and the steam come into the reactor. They get into a very hot place, a furnace fired, in our case, by natural gas, gets very hot, creates the reaction to make syngas. And then as the gases are exiting, this is a pipe inside of a pipe. The gases on the inside give up their high temperature heat to the incoming colder gases to warm them up. And thereby, we're conserving energy. So we've designed this particular reactor to be extremely efficient, and especially on heat and water. We don't use any extra water. We only make enough steam to run the reactions. So this is a very productive way to do this. It makes our technology very scalable, because the reactor, in this case, these reactors are only 2.5 inches in diameter. And if we want more capacity, we put more reactors in a furnace. The furnaces are typically, 4 or 5 feet in diameter. Mm-hmm. We're using circular furnaces right now, but so you can put a lot of these tubular reactors into a furnace. So if you want more capacity, you put more tubes.
Okay, and not wanting to go back, so also being conscious for time, but the temperature that you have in this reactor is similar to the one you showed earlier. So it's around 900
yes.
C as well.
Yeah.
Okay, that kind of okay.
That's right. It's in the mid to upper 800s of centigrade.
And you're routing it back to also recover that heat. I mean, this is interesting because just on this channel we've had quite some discussions about heat exchangers, and mm-hmm. also them being a decisive factor in efficiency of systems. But this is not a separate heat exchanger, or do you have that in the system as well?
That's right. There are other heat exchangers. For example, the heat that comes off of the furnace goes out of flue stack.
Yeah.
And we recover that heat, and that's how we make steam from water. So we try to use every BTU or joule of energy that comes in. So the furnace makes heat. The heat that leaves the furnace is collected by making steam, and that's where the steam part comes in. We put cold water in, and then generate our own steam in the process. And then you're right, Stephen, this is intended to be a very efficient way to collect up heat that we went to a lot of trouble to make this very hot temperature for the reaction to occur, and we don't want to throw that away.
Exactly. Okay.
The large scale SMRs, the guys that make, by the way, we're talking about a capacity here of 1,000 kilograms, 1 metric ton, or 2 metric tons. A big SMR, a big industrial SMR, the way they are embodied now, make hundreds to 1,000 tons a day. So we're a
1,000
lot
tons.
smaller.
Wow. Okay, that is.
Yeah, and so we're doing this on a very small scale, and they have they take advantage of a different feature. And they don't try to conserve the heat quite as much as we do, because what they do with their extra heat is make a lot more steam, and they can sell the steam to the industrial customers through their pipeline.
All right. Okay.
So we don't have industrial customers that we're sitting next to, so we can't sell steam. Therefore, we have to be very economical with all the BTUs we generate from the furnace. So all the heat in the process comes from the furnace.
I do remember talking to a gentleman who was also thinking about implementing some hydrogen applications, and he said, whenever he does that, he looks for proximity to refineries, because there you have enough hydrogen, as you've explained.
Exactly.
And that, But tell us more about. So you say you make the smaller systems that can be put also not in refineries. That's correct?
Not in refineries. Let's talk about where they're going to go.
Yeah.
Oh, first of all, we've done this on a pilot scale.
Yeah.
And if you can see my background on Zoom, that's the actual factory, which is nearing completion, the first of our small factories. But this is a pilot scale operation, a 1/5 of 1 ton a day, which we built in Albuquerque, New Mexico.
Okay.
And we did that to prove out all the individual componentry. And we also, at the same time, designed it as a modular system. So you see that big metal framework that came in on a truck on its side, and we tipped it up and put it in place.
I was wondering when I saw that first. That looked like a 40-foot container, basically. It is. Okay,
exactly right. That fits on a big flatbed truck, and the modules that we have now in the full scale plant have all the other ancillary equipment, such as these things over here and these things over here. They're in a framework like the main reactor is as well. So there's actually 3 truck-based modules that come in on their sides, and we stand them up.
Okay, Greg, please. So I'm a little bit conscious of time, and we wanted to get to the carbon intensity part. So maybe you can quickly segue to that, because we're really curious to understand that part, which you've mentioned now. Yeah.
Okay, good. Well, so just a couple more comments on the centralized hydrogen. Because the plants are so big and they have a large investment, any customers that are far away have to get their hydrogen by liquefaction at the factory and then transport by truck. Some of these transportation routes are 1,000 miles. So that's the centralized production model with big factories. And this is what I just said. If you're lucky, if you have a pipeline. If you don't have a pipeline, I think it's important to note that it's $1 to $3 a kilogram to make the hydrogen, but for high volume liquefied shipping could be as much as $14 of shipping cost. So this is the lead in to carbon intensity, and why it's important to mind not just the carbon intensity of the process, but the carbon intensity of the delivered product. That's a very important point. And in low volume sales are, with liquefaction, are paying maybe as much as $20 a kilogram. Our model is build a lot of these littler hubs so that our production and our usage are very close by. We won't, we'll have a radius of delivery that's relatively small compared to the big centralized industrial plants. And this is now the notion of carbon intensity centers a lot around shipping as well as manufacturing. So I'm just going to skip through this. Carbon intensity takes into account, get this out of the way, the entire life cycle. So the primary energy production, making the fuel, in my case, it's methane, transporting it by a pipeline. And then here's the reaction part. This is just my little module compared to the big industrial SMRs. But then once you make the hydrogen, you have to compress it, maybe liquefy it. You have to move it, store it, and then you have a use for it. And so there's carbon expended in every one of these steps. And people tend to think that just the production is the most important part. It is an important part, but it doesn't necessarily dominate the landscape, especially with long distance transportation. Now, the carbon intensity is measured two different ways. One as grams of CO2, that E means equivalent, for each megajoule of energy that you created, not energy that you used, but energy that you created. And this is the energy-based definition of carbon intensity. And then there's a mass-based definition of carbon intensity, which is kilograms of CO2 generated for each kilogram of hydrogen generated. And you can translate between those two things because kilogram of hydrogen is 33.5 thousand BTUs. Yeah. So I'm an engineer. We use English units.
It's 33.5 kilowatt hours.
Yeah. It's like the same thing. Same. So there's the definition of carbon intensity. And now the most important thing to talk about now is what does that mean and where does it put things? Yeah. So using that entire life cycle of cost of fuels, these are fuels for mobility. Yeah. Here, the diesel equivalent on that basis is 190.
So that's 190 grams of CO2.
Grams of CO2 for each megajoule of energy created.
All right. Okay, so we're talking megajoules. Okay.
Right? How much CO2 did you make?
Yeah.
Per energy, right? Because it's normalized by the energy.
Yes.
So now let's look at grid power electrolysis. This number is the California number. We didn't calculate this. This is California's number. So if you use grid power, which means generally either nuclear in California, but that's being phased out, or natural gas turbines, that the carbon intensity number is 164. This number is very variable depending upon where you're getting your grid electricity. For example, in Kentucky, where the energy source is coal, this carbon intensity number is in the 500s. So it's much bigger for the older, so-called, sort of dirtier sources of electricity. Now, the central SMR guys, the big steam methane reformers, they use natural gas and they liquefy. That liquefaction is very expensive. It costs 45 grams per megajoule on this scale. So it's almost the same as on-site electrolysis. This isn't cost, remember, this is not the cost of it.
Yes, I know. It costs in terms of grams per CO2.
Cost
that's
right.
CO.
It's carbon burden, right?
Yeah, carbon burden. Yeah, exactly. Yeah, okay.
So central steam methane reforming, which uses a gas delivery, saves that compression energy, that 45 grams per megajoule. And then where we come in, because of our efficiency and our delivery radius, we make natural gas with gas delivery at 110. So we can actually compete extremely favorably with the big plants because of the efficiency of what we've designed. And of course, we can actually do better than electrolysis on grid power. Now, electrolysis on renewable power is very good. That's 11.
Yeah.
So there is a carbon footprint to renewable power. It's not zero. So the real, now the problem with on-site electrolysis from renewable power is intermittent. A lot of it's intermittent, and there is not very much built up storage for industrial scale energy.
Okay.
So as that comes online, this will become probably a prominent part of our world. I don't doubt it, and I think that's a good thing for the world. I live in it too. And but what we've been thinking about of late is using renewable natural gas. RNG is renewable natural gas. And what is renewable natural gas? Think of a farm. And farms create the farm animals, particularly the dairy industry or the meat industry in the United States, creates, they grow cows, they eat grass, and they make an awful lot of manure. If you let the manure sit out in the field, it degrades to methane. So methane escapes, and methane is 80 times more potent than CO2 as a greenhouse warming gas. 80 times more.
Yes.
So if you collect the methane and you collect the manure and you ferment it into CO2 and methane, now you have something that has reduced the carbon intensity of that material by 300 grams per megajoule.
Yeah.
So this is the value of RNG. If we used all of our natural gas coming in was renewable, gives us a negative 300 score on carbon intensity.
Okay.
And if we use just 30%, that brings us to zero.
Okay. So
now,
if you allow me to chip in there, as a matter of fact, I mean, if you travel to certain areas in Europe, you have quite a number of these farms where they actually, catch the methane and use that for generating electricity, run on engines on that. So that will be the kind of same source you're talking about. It's essentially big containers with domes on them, and then, they pipe off the gas at the top. Yeah.
Yes. Now, there's a couple of ways to go at it, Stephen. One is you can actually use the gas, which has to be cleaned up a good bit because it has other things in it, right? It's not just pure methane. But in the United States, and probably in Europe too, there is a trading system for buying and selling credits for use of RNG that gets tagged with the RNG credit for carbon. Yeah. So right now, instead of building our sites where farms are, we're going to buy credits for that renewable natural gas, and there's a price to pay for that, but it gives us this terrific performance on carbon.
Okay, Greg, that I must say. Okay, the thing is, we've gone a bit far on our time, but this was because it's that interesting. I mean, I think it's a pretty strong statement. That we see here, that you can turn carbon negative using steam methane reforming. That's what I have learned here. Yeah. Okay. Wow.
We can do that, and BayoTech is on track to go from where we are right now is our 110, and we're on our journey to zero.
Okay. Well, I would say that is news. So this is something more to talk about. Maybe we can even learn a little bit more. Thank you for taking us through your reactor to the dairy farm and somewhere near zero or even below zero. I think that was extremely interesting. If you want to know more about BayoTech on Hyfindr, you can find some of BayoTech's wonderful products and also other things that you need to make the hydrogen economy work. You can get into contact with people like Greg, and if you're interested in growing the hydrogen economy, maybe you even make a contribution here or there, either by sharing your knowledge or joining a community or just following us on this channel or elsewhere. Greg, it's been an absolute pleasure speaking to you. Thank you so much for your time. Unfortunately, we've already come to the end, but as I thank you, I'd like to thank the audience as well, and I hope you can watch this or many other videos on our channel. Hope you like it, and looking forward to see you once again in another video. Thank you very much, Greg. And thank you.
Thank you, Stephen.
Thank you.